Hey guys, my name is Devon Peticolas. I'm an engineer at an awesome company called Chartbeat. And the first thing I just want to say real quick is this is my first Clojure Conj. It's also my first time giving a talk at a conference, and you guys have been awesome. I know no one here, and feel like I've met a million people in the past 2 days, so you guys are pretty great. But yeah, so this is my talk, 1 million clicks per minute with Clojure and Kafka. Now I know you guys came to this talk based on the title, and you assume it's about how we're going to process 1 million clicks per minute using Clojure and Kafka, and I'm really sorry to do this to you, but the title's actually wrong. The correct title is how not to process 1 million clicks per minute with Clojure and Kafka, and then how to. I'm going to tell you guys a story of how we built this application, because this was the first real product that we built using Clojure as the language to write our consumers off of Kafka. So I'm going to move pretty quickly because I have a lot of slides. You might say that, like an imperative language, I have a problem with scope. But you can go right here, and it's github.com/x/slides, and that's where all the code is, and it's all numbered. So I work for this company called Chartbeat. What is Chartbeat? We're a company that does real-time and historical analytics for publishers on the web. So we tell them things about their visitors. What are they doing? What are they reading? How many of them are there? Are they new? Are they old? Stuff like that. How do we do that? So we have client-side code that runs on their site. So this is an example, gawker.com, someone I can admit that is a customer of ours. All the others you could probably tell from Chrome Inspector. So when a user goes to gawker.com, what happens is our code's running it's a small bit of JavaScript that's running and tracking their state and sending what we call pings to our servers. Now, a ping is the smallest HTTP request we can get away with. It's a GET request going for a 1x1 pixel image, and actually inside of the query parameters of that GET request is all the data that we want about that user at that time. And so we send lots of these throughout the time they're on the page, about 1 every 15 seconds. And together, they're what we call a session. And this describes a user being on a page. And when they stop pinging, they're no longer on the page. So we can tell whether or not someone's there or not. You might say, that sounds like a lot of requests. It is a lot of requests. So our patterns, because we mostly serve European and US clients right now, our traffic patterns have this nice little curve to them. And this is a typical Tuesday. We get up to 250,000 requests per second. This was March 22nd during the Brussels attacks. So we went up to 300,000 requests per second. So I think Chartbeat has this really unique quality where if you are, say, a person who's on call at a normal company, you get paged when something goes wrong with your servers. If you're a person on call at Chartbeat, you get paged when something goes wrong anywhere. So what does this data end up looking like? We end up turning into dashboards that look like this, primarily. This is gawker.com's dashboard or a screenshot of it, and it shows you how many people are on the site and what pages they're on, stuff like that, where they're coming from. The dashboard that we're going to be building in this talk is actually slightly trickier. It runs on top of their site. It's that little blue thing in the top right-hand corner, and when we open it, you get an overlay on top of the site that shows a little tiny pin on every single link on the page and ranks them based on how many clicks each one of those articles is getting. If you were to click on one of those pins, it opens up and it can say, okay, this position is getting 3.3 clicks per minute, and you get a nice little historical graph of what that is over time. So if I were to summarize this in a user story, because I have drank the Kool-Aid, I'm a big believer in Scrum, or as my product owner would write it, Adam in the bottom right-hand corner, looking dashing. As a homepage editor, I want real-time clicks per minute on each of my articles on my homepage, and I want a historical graph of each of the clicks on each article on my homepage, so I can make informed decisions about the content on my homepage. Now, the important word there is real-time. That means we can only have a few seconds of delay. We need to be doing this pretty quickly. So how do we track a click? That's probably the first question. So as I was saying, all these pages are sending pings. Now, you might think the best way to track a click is to actually track when a person clicks on a link, but what we found is it's actually much more consistent to track after they've already arrived on the next page. Since we only really care about internal traffic anyway, we know there's going to be pinger code on the other side. So what we do is When that happens, when a person goes from, say, Gawker.com's homepage to an article page, there's what we call an HTTP refer. It is spelled incorrectly in the spec. That is part of the HTTP spec with only one R. So if you look at this, you can use the HTTP refer to say, okay, we came from Gawker.com's homepage, and the current page is Gawker.com/article1. We can say there was some page movement from between those two pages, and we can ping those both up. And the other thing we're going to ping up is the time that we've been on the page. So this is important because, as I was saying, we're going to send lots of pings during a session. So what we really only care about is the first ping, the one where the time on the page is 0, because that way we're not counting a click more than once. So how are we going to deal with this when we have so much traffic to begin with? So in comes Apache Kafka. So what is Apache Kafka? Kafka is a fast, high-throughput distributed message bus, basically. You can kind of think of it as, or a commit log is actually what people often call it. You have producers that write to it, and you have consumers that read from it. You might think of something like RabbitMQ when you see something like this, but it's actually slightly different in a really interesting way. With like RabbitMQ, what happens is it's a queue. You dequeue off the queue, and it goes to some it's pushed to some random consumer, and that consumer processes that message. With Kafka, a consumer subscribes to some partition of the data that you want, what we call a topic, and that consumer gets to track where it is in actually a log. So this is why people call it commit log. The producer is writing to this log on one end, and the consumer is reading up this log on the other end. And that gives us a couple really cool properties. One of which is we can kind of have order to our data, which you wouldn't really have that kind of guarantee if you were dequeuing, and it might have to come back. Another thing that you have out of this is that the data can be replayed depending on how much of that log you want to retain. There are people who will retain an entire day's worth of logs. That's good if you have an outage or you need to correct some data, or if you just want to have something else that reads in a different way. So what's our new pipeline look like? It looks something like this. So we have a customer who's interacting with Gawker.com's homepage, and on that page we have our JavaScript running that's sending pings. Those pings are going to go to an AWS Elastic Load Balancer. That's going to do what it sounds like it's going to do. It's going to load balance. It's going to send to a bunch of what we call front servers. Each one of these front servers is running Nginx and a small server written in C++ that all it does is it consumes messages from over HTTP and then produces them. Well, message packs these pings first. Message pack is a type of serialization of JSON. Gets the size down a little bit, and then it writes it to Kafka, to one of the brokers. And then on the other end, you have consumers that are reading from Kafka. Now, there's an interesting thing that's happening here. The producers can write, what's inside of this broker, you see these partitions. Each one of these is like a log, and it's appending on one end, and the consumers are reading from the other. Now, a producer can write to any partition that it wants, and the way it decides which partition it writes to is based on what's called a partition key. You choose some way you want to partition your data in advance. So the way that we're going to be partitioning our data in this talk is based on the customer. So what that means is all of Gawker.com's data is going to be going to the same partition. On the consumer side, a consumer subscribes to a partition. So every partition only has one consumer that's subscribed to it, and what that means is that at any given time, it gives this nice little quality where you can now maintain some sort of state in that consumer about that partition. It's pretty cool. You can imagine this is like super useful for caching, because all of a sudden you have like a much smarter way of caching. Or you could do some really interesting things where you kind of join a stream onto itself, which we're going to get into a little bit later. So what's that code look like? So this is our first iteration of our consumer. We're going to use something called CLJ Kafka. It's a very common library for dealing with Kafka. And this is kind of how this is what our code's going to look like, keeping out the details of how we're writing to a database. So the first thing we're going to do is we're going to create a consumer object using this consumer function. It's going to take a bunch of options. It's also going to take which topic it's consuming from. Then we're going to use this messages function to get a lazy sequence of messages from the consumer from this topic. Then we're going to iterate over each one of those messages. As I was saying, those messages are message packed, so we're going to unpack those messages. Now, this is an interesting thing to note real quick. This is the highest CPU utilizing part of our program right now. this is what takes the most crunch. And then we're going to step through each one and say, is it the first ping? Because that's the only one we care about. We only want to count 1 click per session. And then we're going to identify the source, which was the HTTP refer, as we were saying, the target, which is the current page, as we were saying, and the minute that it happened, and just increment once in the database. Sounds pretty simple, right? Oh, we OOM'd. This poor corgi. I love this guy. I don't know what was going through his mind. So what happened? So the issue is actually, and I did this, the issue is actually that we are holding onto the head of a lazy sequence. I don't know if you guys are familiar with this, but when you have a lazy sequence, so this is an example of a lazy sequence. We have this function called lazy nums. It returns a sequence which is, every item is an increment on the atom up there called counter. If we were to iterate over lazy nums declared inline inside the doseek, what you see is 1, 2, 3, 4. And then if you did it again, you would see 5, 6, 7, 8. That's because you're mutating the atom. However, if you were to assign lazy nums to some sort of symbol and then iterate over that, it would hold on to the previously iterated over things. It would cache it. And this is just a strange property of lazy sequences. Maybe it's not strange to everyone else. It was strange to me coming from Python and being used to generators. So what's happening here is we're holding on to an infinite lazy sequence. This thing's just going on forever, which is why we're OOMing. So the workaround for this is not beautiful, but it's doable. We just iterate directly over the lazy sequence. So we're good now. We're iterating over the lazy sequence. We're not going to OOM. But we're running really, really slowly. I love this guy. He's so good. So why are we running so slowly? It's because, well, we're incrementing the DB every single time. If you think about it, say Gawker.com's top article is getting 100 clicks per minute. That means we're probably incrementing 100 times more in the database than we should be. That's way overkill. There's got to be some way to reduce this, right? And this is when you get into a very common pattern that you see in Kafka consumers, which is that you're going to batch those messages. So this is an example of our batching code. So we have our messages, which is a lazy sequence. We're called partition on it and partition out 5,000 messages at a time, which is for us fine considering how many requests we're getting. And then we're going to, instead of iterating over individual messages, we're going to iterate over the batch. Each one of those batches we're going to unpack using map. We're going to filter out to just the first pings using filter. And then we're going to, actually, I can step through these. Map, filter. Then we're going to group this data by the HTTP refer, the path, and the minute. And again, this is the source, the target, and when it happened. And then we're going to iterate over the grouping, that data, the source, the target, and the minute, and the messages, and then increment that count in the database. So now we should be good, right? We no longer have this issue with our writes to database. We've reduced them massively by doing this batching. Oh, but we're really inconsistent in the way that we're using our CPU. Now, what does that mean? Just like this poor corgi, I don't know if you guys saw there's a theme to my GIFs, by the way. I live in New York, and I can't have a corgi in my apartment. But so just like this poor corgi who's going up and down, our CPU is going up and down. And that's usually a bad sign. Really what we want is something that's much more level, because that means that we're properly, there's nothing blocking or lockstepping there. So for both our CPU and our corgi, we want to keep them on level ground. So let's talk about how Kafka works. And I'm going to say right now, as I show you this slide, there's a note in here that says to do, replace this slide. Sorry, it's a little bit of a mess. So this is roughly how it's working. So we have our producers, and they're writing to our brokers. And it can write to, it's actually a push when it's writing to the broker, because the broker can just, it has this moving window, it doesn't really care. But on the consumer side, it's actually a pull. It's not being pushed by the brokers. And the way that's actually happening is inside that messages function that we were using, there's something called a KalkaStream object. And inside that KalkaStream object, there's essentially a queue. And that queue has some number of chunks, and each one of those chunks is some number of bytes of data. And whenever we're not at full on that queue, we're going to go out and do a pull. We're going to fetch and then come back with data from the brokers. So you can imagine there's now this situation that we can get into where with our partition function here, partition doesn't really return a lazy sequence of lazy sequences. It returns a lazy sequence of fully realized sequences. So what's happening here is to get those 5,000 messages, we're actually going to network to make sure that we have them there. And so until we have those 5,000 messages, we can't start doing the most CPU-intensive operation, which is unpacking each one of those messages. And what we're doing is we're just lockstepping network into CPU, and then network into CPU. And this is why we're getting this weird pattern. And the way we can fix this doesn't look that crazy. Instead of using the messages function, we're going to use this create message stream function, which is a very, very, very light wrapper on top of the Java function that does the same thing. And it returns what the Java API usually works with, which is a KalkaStream object by itself. And that is exposed as a Java iterable. So because it's Java iterable, we can just use take on it, and take will return a lazy sequence. And then we can start unpacking our pings. Now, that group by down there is going to force out the laziness, but what this allows us to do is pull from network as we're unpacking at the same time, and now we have this nice balance. And you might think this isn't happening concurrently because it's a single thread, but it's actually not, because the message stream object has its own threads that are going out to network to fetch data. So this really is a concurrent operation that's happening, just using a lazy sequence, which is pretty cool. You might be saying, Devon, like, I know about concurrency. I write Clojure, man. Come on. Clojure has these awesome things called channels, and you should be using a channel here. And I would tell you, you know, you're kind of right. You could use a channel. And if you did use a channel, it's really easy, because there's already an exposed function in core async called onToChan that takes a Java iterable and turns it into a channel. And all of a sudden, all of your messages are in channel, and you can put a transducer on them. And then you can get out batches from your transducer. So this is essentially the same thing, except there's this weird underlying thing that's happening, which is that onToChan is functioning as a Go loop, which is going to wait on the Java iterable and then write into the channel. And it's going to park when it writes into the channel, but it can't park on the Java iterable. It's just sitting there. So what you're ultimately doing is you're just locking a thread against the consumption side of things. So this is actually not, I mean, it's nice, and there's places where this is really useful. There's times when you want things as channels, especially in multi-threaded situations, but it's not that helpful for us right now if you're just going for raw performance. So you might be saying, what do you mean multi-threading? So multi-threading is pretty important with writing Clojure consumers, and it's pretty easy too. So there's a slight tweak on the function that we're using to get our stream object. It's now create message streams. This creates 4 Kafka stream objects, and we can just iterate over each one of those, spin up a thread, and do the exact same thing we were doing before to take messages from that. So you should be doing this when you're writing a consumer, and this is actually how you get the most out of your consumer. Now, when you have multiple stream objects, what you need to keep in mind is that each one of those streams itself acts basically as a consumer and has its own internal queue and matches up against one of the partitions. So if you are going to be doing this, there's a magic function that I don't know if this is right, but it works really well for us. The number of partitions you have should be equal to the number of processes times the number of KalkaStream objects times the number of consumer fetchers, threads, which you can configure inside the consumer. I'm sure someone who's optimizing things later will be happy with that. And this is something I should just mention real quick. There is a new consumer that's considered beta quality in Kafka 09. One thing it does offer is much better ways of dealing with committing to the brokers. I'm not focusing too much on committing on this talk because it can get really complicated real fast. But I would say if there's some dicey situations with the high-level consumer right now, which is what we've been talking about, and this kind of takes care of a lot of those situations, but it does lockstep you against network. But I would recommend using this for, when you really don't want any data loss. So how are we doing? We're doing really good. We have a successful application. Everyone's happy. We're having some beers at Chartbeat. Everything's great. We're all launched. We're good. But then comes product. Adam comes in and he says, Devon, look at this thing. This is really cool. But, when I look at this, I think I see there's getting 3 clicks per minute on this position here, or in this article right here. But what does that mean? Sure, that's like doing pretty good on the page. And the thing to the left is doing a little bit better. But how do I know the thing to the left's only not doing better just because it's in a bigger position? And the thing over here is not doing as well because it's in a smaller position. how is this doing compared to what I would expect it to do in this position? Can you give me position metrics as well? And I go, sure, Adam, sounds easy. So what's our new user story? Our new user story is now, as a homepage editor, I want real-time clicks per minute on each article and its position on my homepage. I want historical clicks for each article and its position on my homepage. And that's so I can make informed decisions not just about the content on my homepage, but the arrangement of the content on my homepage. And this is actually like a really big deal for homepage editors and publishers. It's exactly like there was an editor who used to sit there and edit, the New York Times paper, like the front page of the paper, to make sure that people would, pick one up and read it. This is a very big job where there's someone sitting there all day who's using this tool, who's basically just making decisions about where the content lays out constantly, all day, as new stories appear. So how are we going to get position data? So this is where things get kind of crazy. Before, we were just using the HTTP refer to say we went from page A to page B, from Gawker.com's homepage to Gawker.com/article1. Now we need to get position data, and we can't consistently use cookies. The reason we can't is because under EU laws, for example, you have to say that it's okay that you're using cookies. There's plenty of people that don't have cookies on the browsers. I know lots of you out there probably are those people. And so what we do instead is that we send what we call a Hail Mary ping on the click event. So a Hail Mary ping is exactly what it sounds like. It is just like a Hail Mary pass. We don't know if it's going to make it, but it generally fails with a pretty evenly random distribution. And what that lets us do is it lets us say, okay, if I saw 2 clicks from page A to page B in position 1, and 3 clicks from page A to position 2, then the 10 clicks I actually saw go from page A to page B, I can say 4 of them go to position 1 and 6 of them go to position 2. That's what my data scientist calls imputing. I don't know if that's the right term, but what that means what that requires of us, that means that we have to retain that data somehow. We need to join the stream onto itself to join these Hail Mary pings with the position data against the click pings. So I'm not going to get too much into the slide because it's kind of messy, but this is our new consumer. The biggest difference here is that instead of writing to the database, we're taking that grouped click data and just storing it as a map, and then we're taking this position data and we're creating a bunch of these position maps. And then we're storing those position maps inside of some sort of data structure to hold on to it. And right now that data structure is a vector. And so there's 3 important things that this vector is going to have to be able to do. 1, we're going to have to be able to add new positions to the vector. 2, we'll have to be able to decay out old positions because we want it to be a moving window, say the past 5 minutes of data. And 3, we're going to want to be able to look up what the matching data is. When we say there was a click from page A to page B, we're going to want to say what were all the positions that we saw for clicks that went from page A to page B. Did that work? That did not work. There we go. So this is what those functions are going to look like with the vector. Adding new positions is just going to be, conjuring those positions on. Decaying the old positions is just going to be a drop while. And pulling out the positions that match is just going to be a filter. Pretty straightforward, right? Oh, but we're going really slowly again. Why? Oh, my God. My favorite one about this one, by the way, is that guy in the back right corner that doesn't realize what's going on. He's just dumbstruck. He never knew that door opened. So why is this going so slow? Well, so appending onto the end of the list, that's an O of K operation for K items that you're adding onto the end. Pretty simple. Decaying old positions using a drop while, well, that's O of N because it's a vector. You can't pull from the front very well. It's append to the right, pull from the front. And getting the matching positions, that's actually the worst. That's O of N, but the thing is, this is the thing that's being called the most. This is the thing where every time we're writing the database, we need to get the matching position data. So this is the thing we really need to optimize for. So how are we going to do this? In comes Clojure data priority map. You might be saying, what is a priority map? So a map usually refers to a hash table. And priority usually refers to a priority queue, which is generally implemented as a heap. Now, with a hash table, you have O of 1-ish lookup and O of 1-ish insertion. And with a priority queue, you have O of 1-ish peaking at the top of the queue, whatever the highest priority thing is. You have O of log n insertion and O of log n removal, or popping off the queue. So a priority map is when these point to the same data. And it's really cool. What this lets us do is it lets us create a map where we assign some sort of priority to each one of the items, and now insertions into our map is going to be O of log n, removal from our map is going to be O of log n, and lookup on our map for the key is still O of 1, which is really, really, really awesome. And the one slightly more complicated thing about how we're going to do this data structure is we're going to have each one of those nodes, instead of being a position itself, it's going to point to a queue. So the way this is going to work is the hash table is going to be the page A to page B. The priority, so the queue that we're pointing to is going to be all the position data that within our moving window that we want from page A to page B, all those positions. And then on the priority queue side, it's going to be organizing itself based on the oldest item in each one of those queues. So that sounds really crazy, and you must think, like, how on earth does this get implemented? It's actually really, really, really simple with this library. All we say is priority map key fn by, and we look at peaking on the queue. So that's each one of those queues. We're going to peak the first thing. That's O of 1 because it's a queue. We're going to look at the timestamp, and then we're going to sort them all by less than. So whatever's the toppest priority in our priority map is always going to be the queue with the oldest item in it, which is pretty nice. So what do our new functions look like? Adding a new position, or adding new positions, it's just going to be a pretty simple reduce with an update onto the positions. And the only weird thing is that whenever there's nothing there is we're going to have to create a new empty queue. Decaying old positions, this is a pretty fun one. What we do is we create a loop, and we keep looping, peaking at the top of the priority map, and then peaking at that queue and looking what that timestamp is, and that's always going to be the oldest thing. So we just keep doing this until we've decayed out our window. And when we need to get rid of an item, then we pull out that queue, pop off the end, and reinsert it. And then getting the matching position data is going to be really simple. It's a map. It's just a get. So the runtime for these is going to be something like O of k times log n for the adding new position data, which is slower, but not that big of a deal. Decaying old position data is going to be the number of things decayed times log n, which is probably faster. And then looking up the position, which is the most called function of all, is going to be O of 1 now. So runtime is way better. We're super successful. Look at this guy. So this is what it was before we had position data, and this is what it is after we have position data. Now we can see other articles that were there, and we can see what the typical would be, and we can say that this is doing fine, but that story that was there earlier was actually much better. So what have we learned? So the first thing is beware the head of an infinite lazy sequence. I think this is actually something you could run into when doing any type of Clojure stream processing. Batching whenever possible is a great way of handling data. It lets you reduce network calls. Don't lockstep your network and your CPU. Embrace the laziness of Clojure. Priority maps are the bomb. Multithreading when possible. And writing a consumer in Clojure is actually pretty easy. If you think about it, we started with something very different, and we went through lots of refactors, and we ended up with something that didn't look that insane. It's pretty nice. And when you think of what it would have looked like in Java, it's not that fun. Like, I've written Java consumers too, and they're awful. Like, really just, I mean, maybe I'm biased, but they're the worst. And it's funny, because when you look at every one of these, stream processing frameworks, and you look at what they're written in Scala and Clojure. And when you look at their recommended APIs, they're all Java. And this is because they expect everyone to be using Java. It's an easy language. But what's nice about that is it means that if you want to be writing with Clojure, you're always going to be a first-class citizen when you want to be doing something, because you're just interfacing with Java. Java interop is fine. It's so easy. So this is great. So I think what I really want to get to here is that Clojure is not that, it's not that Clojure is good for Kafka. Clojure is really awesome for general stream processing. I actually think this is kind of the future of this language. I know a lot of people who come to this conference are people who don't get to use Clojure in their day-to-day job, and they're kind of looking for reasons to use Clojure, right? And there's all these reasons to use Clojure. You can use it to write web servers. You can use it in ClojureScript. You can make apps with it. But all of those spaces have like fairly strong competition. Stream processing really, really, really sucks. Like, writing in Java is not fun for this kind of stuff, and Clojure is just a Java interface, and then you're processing lazy sequences. It's a Lisp. It's perfect for this. So I'm really hoping that, 10 years from now, when people think of Clojure, it'll be the same thing as like when people think of Ruby, they think on Rails. When they think of C++, they think of games. When they think of Scheme, they think about writing Scheme interpreters. Like, I really think that Clojure's future is going to be stream processing. Thank you.